Alright, intro to the method of multiple scales, sometimes called MMS. Okay, so let us proceed with some very elementary calculus. Okay, elementary calculus review. So let us say x is equal to cos t, y is equal to t square, and g is equal to f of x and y, some f. What is dg dt? It is del f del x into dx dt plus del f del y into dy dt, right? So in this partial derivative, the dependence on y is ignored. In this partial derivative, the dependence on x is ignored. Okay, these are interesting calculus operations, this one and this one, and so we are left with del f del x, so dg dt equals minus sine t plus del f del y times 2t. Okay, very basic. All right, there's just no doubt that this is correct. Okay, now what we do in the method of multiple scales is the following. Instead of thinking x is a function of t, we think of x as being some other function of t0, t1, t2, and so on. These are the multiple time scales, and separately we write, in this case, t0 equals t, t1 equals epsilon t, t2 equals epsilon squared t, etc. Then dx dt equals del capital X del t0 times 1 plus del capital X del t1 times epsilon plus del capital X del t2 times epsilon square plus dot dot dot. Okay, that is how it works. Very good. Using this expansion, using this sequence of multiple time scales plus an appropriate expansion. Multiple time scales plus an appropriate expansion, we will be able to develop useful approximations for several different problems. Okay, so we will start with the simplest problem, which is x dot equals minus epsilon x sine squared t plus x. We have looked at this with averaging. We have done it. We know the answer. X dot is basically equals minus epsilon xa by 2. This can also go to higher order, but for hand calculations, first order is much easier than second order. So we will now do this with the method of multiple scales. Here we are. So we have x dot is equal to minus epsilon x sine of t plus x. We write x is equal to capital X of t0, t1 and so on. I don't need to do more because I'm doing first order only. I have x dot is equal to del x del t0 plus epsilon del x del t1, and I don't need any more. Of course I should specify here, so let me do that. t0 equals t, t1 equals epsilon t, etc. Okay. My next step is to say capital X, which is t0, t1 and so on, is equal to capital X0 of t0, t1 and so on, plus epsilon capital X1 of t0, t1 and so on, okay, plus dot dot dot. So note, two steps. Multiple time scales, expand capital X. These are our two steps. Okay, let's see how that works out. So we have x dot is now equal to del capital X0 del t0 plus epsilon del capital X0 del t1 plus dot 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 plus epsilon del capital X1 del t0 plus epsilon del capital X1 del t1 plus dot 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 plus even higher terms. And you will notice that this is already, we'll drop it because this epsilon and this epsilon make epsilon square. Okay, therefore we are left with a nice package here. We have del x0 del t0 plus epsilon del x0 del t1 plus epsilon del x1 del t0 equals epsilon x0 plus epsilon x1 plus dot 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 plus times the sine of t plus x0 plus epsilon x1 plus dot dot dot. Okay, now remember, on the left hand side we have dropped order epsilon square, so this is easy. Over here also we have to drop order epsilon square, which just means we will have epsilon x0 the sine of t plus x0, except I have made one mistake. Please notice this must now be written as t0. Okay, all right, other than that no problem. So our equation is now clear. We have del x0 del t0 plus epsilon del x0 del t1 plus epsilon del x1 del t0 is equal to epsilon x0 the sine of t0 plus x0 plus order epsilon square. There is an order epsilon square on the left side also, but I can bring it to the right side and absorb it, so I'm not writing it separately. This is our equation. This is what we have to handle. Let me put it inside a yellow box also to help you realize that the first part is done. Okay. All right. What happens at order 1? Del x0 del t0 is equal to 0. If this was an ordinary differential equation, then x0 would have to be a constant. But now, because this is a partial derivative, something very nice happens. What we conclude is that x0 is some arbitrary function of t1, t2, and so on, which we will write as x0 is equal to a of t1 with, some understanding that actually the rest are implied. So x0 is an arbitrary function of t1. It can be anything, sine of t1, cos of t1, whatever it may be. All we know is that it does not depend on t0. Okay, that is what we have got from order 1. Very good. At order epsilon we have this, this, and this. Okay, so let's write that down here. I should move to the left, scroll up a bit. So if I remember correctly, I have del x0 del t1 plus del x1 del t0 equals minus epsilon x0, the sine of t0 plus x0. Sorry, no epsilon. Epsilon is taken care of. This is what I have at order epsilon. Okay. Now x0 is a of t1, so this is del a of del t1 plus del x1 of del t0 is equal to minus a of t1, the sine of, have I got sine squared? I think I had a sine squared and I have made a mistake. See, without the sine square I'll have to go to second order, and I have backed myself into a situation where I will have to do second order, but because I can correct things, I mean sine square, and here I mean sine square, and here I mean sine square, etc. Okay, and so over here I mean sine square, and I have sine square t0 plus a of t1. Very good. Del x1 del t0 is equal to, therefore, minus del a del t1 minus a, this is t1, of t1 sine square t0 plus a of t1. Notice that again this is a partial derivative. Okay, so as far as thinking of this is concerned, we can think of the t1 as a parameter. This is some function not dependent on t0. Not dependent on t0. This part not dependent on t0. Only this part depends on t0. Okay, so as now you can anticipate, yes, this right hand side, which I will put in a let me see, a red box here, this right hand side can be thought of as a non-zero, potentially non-zero T0 average plus oscillating with T0 zero mean. This part does not cause a problem here. If this T0 average is, let us say, B, then over here we will basically have del x1 del T0 is equal to B. So we will have del x1 del T0 is equal to B plus oscillating part with zero mean, and this will give me a B T0 and my expansion breaks down. Okay. However, not all is lost, right? What is important? A was a completely arbitrary function of T1. I could choose anything. I will choose A1 to be such that the expansion is valid for as long as possible, right? And I will choose A1 to be such that this average, the T0 average, is 0. The T0 average happens to be minus del A del T1. Why? Because it doesn't even depend on T0. So its average is whatever it is. Over here, the average of this holding T1 constant, this one constant, is half. So minus A1 by T minus not A1 by T, A by 2, right? I will force this to be 0. Okay, this making this equal to 0 is called removing secular terms. And when you first see it, it seems like cheating somehow. And there are many people who discuss it in many ways. And I just put it in a practical way. I say this is insisting that the expansion remains valid for as long as possible. What is the validity that I am talking about? x0 plus epsilon x1 plus epsilon squared x2. This is my series. In this series, this term must be much smaller than this term, and this term must be much smaller than this term. The moment that condition is violated, it is no longer asymptotic. I want an asymptotic series, right? So my asymptoticness is lost if this becomes big, or if this becomes big compared to this, or if this becomes big compared to this, and so on. So you see, what we end up with is exactly the averaged equation. Okay, let me remind you here. Where is this epsilon from? I think I have made a mistake in sign also. This was a minus. So let me see now. No, that's okay. So the sign is fine. Just a very small final step. Take this over. So we have del A del T1 is equal to minus A by 2. But you see, what have we got? Come on. Here. What have we got? We have got x is equal to x0 plus epsilon x1 and we have got x0 is equal to a of t1, t2, and so on. So dx dt is equal to del x0 del t0 plus epsilon del del x0 del t1 plus, see, x and x0 are close, right? So I will write this as dx dt, and then you see and this one is 0. So here is this epsilon. Okay, that is why we have finally dA dt is equal to epsilon times this, and so minus epsilon a by 2, and that is exactly the same that we got from averaging. I will show you the second order multiple scales for the other equation without the sign squared, but for that I will use Maple.